Good morning, everybody, and thank you very much for joining us today on this presentation. It's not our normal topic of allergens, but it's something I came across about 18 months ago and found particularly interesting, the innovation. So I did actually ask Unox whether they'd actually spoken to regulators about the technology. And I hadn't, so I volunteered to host a webinar as we have done today. I'm not an expert on this topic, we're just hosting it on behalf of Unix. I would please ask that you make sure that your microphone is muted. If you can turn off your video as well, that'd be appreciated. So that we've just got the speakers that are here. Sorry, I'm just letting people in as they come through. I'm going to hand over to Robert Edwards from Unox, who's going to introduce our speakers. He's actually not able to stay for the whole duration. And then we've got Trevor, Michaels and Mario. And then I'm going to host the Q&A. I'd ask if you put your questions into the chat box, and I will pick up on those as well. We will try and get through as many of the questions at the end of the session. However, we will also note them and we will come back to you as well. So sorry, I'm just letting else person in. So we will note the questions, and if we can't answer all of them, I will pass them on to the guys, and then they will respond, and we'll send them out as part of the feedback. After the event, we have our feedback email that goes out. If you can give us the feedback on the event, if you need some more information, you'll get a link to the slides and also a video for additional information. So I'm now going to hand over to Robert, who's going to do the introductions, and I'll be in the background, and you can message me on the chat if needed. I think we're up to about 62. So I'm going to hand over to you now, Robert.
Hi, thanks very much, Caroline. Just a little bit from me. I'm going to do an introduction to Mario and Trevor, who are going to be speaking on behalf of Unox. So massive thank you to Caroline for putting the event on. This is almost the brainchild of a conversation we had about exposure for, Averio, and obviously, it's an educational session. So we want to make it as educational as possible. And we also want to ask as many questions as you can, so that everybody can further understand Averio as a concept. Yeah. So we've got Mario Camerotta, who is our Chief Technical Officer over at Unox SPA. So we're lucky to have him on. Mario has technical knowledge of Averio, and he's going to be happy to answer questions. And we also have Trevor Michaels. Trevor is part of our key account team in the UK, and he's also got a presentation. He's going to talk a little bit about Averio as a concept and how we use it. So I'm going to pass you over to Trevor. Enjoy the session, ask as many questions as you can, and anything that we can't answer on the call, we'll endeavour to be answering after it as well. So thank you.
Thank you, Rob. Good morning, everyone. As Rob said, I'm Trevor Michaels, Key Account Manager. I'm also Sector Development Leader for Hotels for Europe for Unox. I've been with the company for 4.5 years, and I'm just going to give a bit of an insight into the Averio, also known as the hot fridge, which is what we're going to talk about today. My part is a bit of an introduction into the product itself and to Unox, the company, and then Mario will take it on from there and talk further in depth in terms of the actual technology side of it, and take into account how we developed the product itself. So the Averio is a unique piece of equipment that preserves cooked food at service temperature using a combination of precisely accurate temperature and atmospheric control. Something that we believe there's no other like it in the marketplace. If you can go on to the next slide, please, Caroline. So how did the Averio come about? So the big thing with Unox is that we look at our customers' needs and requirements, and we take into account what the trends are within the marketplace. And the Averio was developed over a long period of time, taking into account the reduction of food waste, the need for 24-hour service becoming a more common theme, more nutritious meals, food safety, customer satisfaction and speed of service, the recording of data, food waste and HACCP information, consistency in results, and the food that's being served, and obviously value for money, not only for the customer, but also for the users in terms of energy costs that are rising and going through the roof. Next slide, please, Caroline. Thank you, Karen. So Unox, we are a company that we're founding in 1990. We currently have in excess of 1,400 employees globally. We are a truly global company. We have 42 branches around the world. And our main head office is situated in Padova in northern Italy, just about 25 minutes away from Venice. The company, what's our ethos? Our company has an ethos of providing success to our customers. And we get this from the needs of our customers, and then we provide solutions for those needs. And that team that provides that is a team of chemists, physicists, and engineers that face the challenges of our customers and our marketplace, and then develop innovative technologies to provide the solutions and provide the success to our customer base. We can go to the next slide, please, Karen. So the Averio, the first ever hot fridge, as it was very quickly known as. As you can see, there's two main ways of using the Averio, and we'll talk more about this as we go through. There's an up to 8 hour standard holding procedure, and then there is the vacuum system that uses our multi-day trays and multi-day compressed air system that can hold up to 72 hours. We do this by a constant temperature control, and that's recorded with live data, and also a constant humidity control. And again, Mario's going to explain more about how this works when he goes on to his presentation. Next slide, please, Karen. To give an indication of where the product is used and how, it is used across all hospitality and catering sectors. To give you some examples, as I said, I deal with many hotel chains. It's used widely in hotels, from room service to banqueting to meeting rooms, healthcare, from schools and education facilities right through to healthcare and hospitals. Contract catering, where we have the need to provide manufacturing facilities with round-the-clock menus that are the same as the daytime and the evening time. Restaurants, from your chain restaurants and entry-level QSR restaurants and chains, right through to high-end Michelin star restaurants as well. So it is really a product that can be used across every sector of our industry, and it's been embraced by those people as well. Next slide, please, Caroline. So, as we know, 24-hour food service brings a number of challenges. We have staffing issues, energy costs rising and more energy being used. We have higher quantities of food being cooked, and therefore huge amounts of food waste. So the question was, what if there was a way to serve nutritious hot food 24/7 without the need for a constant team of chefs, a constant array of equipment using energy, and in a kitchen with a smaller footprint? And those were the main questions that were posed to us. Next slide, please, Caroline. And the way that we tackled that was by coming up with the Averio. And as I've talked about, we do a super holding, which is up to 8 hours in normal gastronom trays, or we can provide up to 72-hour holding using our multi-day vacuum seal system as well. And I'll just go on to talk a little bit about that in the next slide, please, Caroline. The models, we have 10 GM11 through to a smaller cube system that is like a little countertop product. As you can see as well at the bottom left of this slide, we have many options where our models interstack with combi ovens and convection ovens. So it gives a real small footprint for a full menu availability for a restaurant. So you can cook from the combi oven and take straight from the cooking going into the Averio. And on the right, bottom right, is the multi-day compressed air vacuum system that allows for the extended holding. Next slide, please, Caroline. And sorry, if you can go on to the next one as well, please. So the multi-day trays, using compressed air, these trays need to be reinforced steel to put up with the compressed air, the vacuum. So they have a reinforced casing around them, but you can cook with these straight into the combi oven. And the next slide, please, Caroline. The lids have a silicone gasket around the top, so it gives a full seal when it is vacuumed. And to release that, there is a small area on the top of it, a little valve that you just pull up, and that will release the air when you want to serve the food from the Averio after cooking. Next slide, please, Karen. So to show you how it's used, you cook in the vacuum tray. You can put the lid into the oven. That will sterilize the lid as well. Straight from the oven, you come out, you vacuum seal, and it can go into the Averio. The second way of doing it is you can cook in your traditional pans, and then you can empty the contents of the food into the vacuum container, then go through the vacuum and then into the Averio. So two ways of using it. Next slide, please, Caroline. These are the different possibilities. So the hot vacuum can be counter-mounted, but it can also be on its own stand with the compressed air unit underneath. And those stands can also be mobile and put on wheels. They all run off 3-pin plugs. Next slide, please, Karen. And the next two slides will give an indication of how it works differently. So this is a traditional method of cooking, blast chilling into the cold room and then taking food around. This is more based around a contract feeder where they're taken to satellite kitchens, or maybe in education where it's produced in a central kitchen and then moved around to schools, etc. So this shows a traditional method. And then the next slide will show the method of using the multi-day system. So the multi-day system uses less equipment, less energy. You have more room in the kitchen, and it shows that it's a more streamlined operation using the hotbox delivery system into the satellite areas that would have Averios, and they serve from those Averios on site. So it's just one example of how this can be utilised, as I say, for more of a central processing and delivery to satellite kitchen areas. Next slide, please. And on to the next one. So traditional methods versus Averio. As we click through, so what you'll see is the Averio versus traditional. This is a traditional method where we go from the start, we cook to the desired temperature, we chill down, that's stored. We then go through back up to the regeneration process, and then the food is then served to the customer. And on the next slides, please. So you'll see the danger zone there. It's going through the danger zone 3 times on the way up, back down, and then to regenerate as well. And next slide, please. And then using the Averio method where we cook, we get to the desired temperature, and then we hold at that service temperature all the way through until we serve the food to the customer. If you click through, please, Caroline. And as you say, the difference there is that we're going through the danger zone just the one time on the way up to reaching our desired cook temperature. Next slide, please. So that's my part. I'm going to hand over to Mario Camerotta now, who's going to run through a presentation which will go into more detail about the technology behind Averio. And Mario, I will hand over to you.
Thank you, Trevor. Please confirm me that you can see my screen.
Yes.
Okay, so brief summary of what I would like to discuss with you today. So I'm gonna start just saying a little bit more about the idea behind the Vario and how this project was born many years ago. Then a quick introduction about what microorganisms are and why it's important for food safety to control them. Focus on bacteria and their threats. Then I'm gonna explain you which are the all the physical influencing factors to bacterial growth, with a particular focus onto the thermoresistance of bacteria. After that, we will focus on all the evidences, the scientific evidences we have that to confirm the intrinsically safety of a Vario. A quick tour into the different regulations about food safety all around the world, and I'm gonna close just mention other scientific facts and results about nutrients and vitamins, in particular degradation inside this machine. Okay, how a Vario would, we started to work on a Vario because thinking about this process, that this is the standard process to store food that, as Trevor has already showed you, pass through the cooking of the food, then we need to chill in the fastest possible way in order to minimize the time the food pass into the bacterial growth range, as I'm going to explain you better in more details later. Then food is stored at -18, for example, and then before to be served, you need to thaw the food and to regenerate it. This process is really an inefficient process for two reasons. The first is energetic. You need energy to chill the food. You need actually a lot of energy to thaw the food and to regenerate it. And all the second reason is operational. You need time to thaw and regenerate food. So the challenge was launched to design an equipment that could really preserve the food at the same temperature at which the food is served. Today, I'm gonna focus more onto the food safety part. I have to tell you that actually the most difficult challenge and we faced was not the food safety, but actually the organoleptic part, how to control the physical parameters inside the cavity of the Vario, as Trevor said, temperature, composition of the atmosphere, so the concentration of oxygen, the concentration of steam, in order to preserve not only the food safety, but also the organoleptic characteristics of the food. But today is more about food safety. We started to work on a Vario in 2010 with the Department of Physics of the University of Parma here in Italy. And as said, the first aspect we analyzed and studied with them was food safety. There are at least 3 different kinds of microorganisms that can be found inside food: molds, yeasts, and bacteria. In many circumstances, actually, these microorganisms are cultivated by food industry to create desired organoleptic effects over foods. A couple of examples: Lactobacillus bulgaricus is a bacteria that transforms milk into yogurt. So food industry wants to have this bacteria and that this bacteria proliferate inside food. Or some molds that can cover some kind of cheese or salami. These molds help to manage the internal humidity of these products and actually protect them from other microorganisms attack. Yeast, for sure, they are used to improve the bread. In other cases, on the other side, it's very important to avoid the proliferation of microorganisms when these microorganisms are pathogenic. Pathogenic means that then they can generate a disease if in human beings and or other animals. Bacteria in particular are quite tricky to be managed. There are 3 reasons for that. First of all, they are very small, so you cannot see them on the food. Second, they don't have any taste. A contaminated food from a pathogen does not alter the taste of a food. Third, and I think that is the most important reason, is the way bacteria and the way the bacteria evolve and proliferate, that follows so-called exponential growth. That means basically, here there is a pretty clear example. If, let's say, at 11 you have just 1 bacteria inside your food, you have a period of time during which bacteria don't proliferate, let's say until 1154. But when they start to proliferate, the growth is really very fast, is exponential. That means in this example that every minute, the amount, the quantity of bacteria just double, okay? One of the most intuitive parameter to describe the growth of a bacteria population is called the duplication rate. And it's exactly the time required to double the number of bacteria. In this example is 1 minute. This is the typical standard growth curve of a bacterial population. You have here the time on the x-axis, and on the y-axis the logarithm of the numbers of bacteria. As you can see, there is a first phase, this white phase here, during which bacteria need time to adapt to the environment, basically. After that, in this light gray part in the graph, is called the log phase, and this is actually the exponential growth. Bacteria now has adapted to the environment, and they can use all the different resources that they can find into the environment just to grow and to increment the number. After that, in this darker gray part, they reach a sort of equilibrium with the environment, and so the growth just stops. And after that, when they depleted all the nutritional resources into the environment, they start to decrease and to die. In food industry, exist many ways to control and many strategies that can be adopted to control bacterial proliferation. One of these is the pH. pH basically is defined as the concentration of hydrogen ions inside food, for example, and it is used to measure the acidity or the basicity of food. The lower is the pH, the higher is the acidity, the higher is the pH, the higher is the basicity. And pH can range from 0 to 14. Just to give you some examples, many different foods are typically acid, like, for example, fruits and vegetables, usually. As you can see here, for example, inside the lemon has a very low pH because it's very acid, pH 2.4. In this range of pH, the orange, I don't think that, okay. Now I think you can see also my laser. In this range, some microorganisms can proliferate, like, for example, molds, as you can easily see in the lemons in your fridge that are usually covered by molds. Other microorganisms on the other side cannot proliferate in an acid environment. like Bacillus cereus, that is one of the most important pathogens that can contaminate food. Other kind of foods have a lower acidity, like asparagus, beans, carrots, mushrooms. And in this range, actually, of pH, many bacteria can proliferate, as you can see from this graph. Milk, butter, and meats have a higher pH. That means that they are neutral or a little bit basic. And also in this case, you can easily have bacterial proliferation. So in this case, pH cannot help you to control microorganisms proliferation inside food. Another important factor that can influence bacterial growth is the so-called water activity, AW, that basically is the amount of free water you can find inside food. All fresh foods, and this value can range from 0, that means that basically there is no free water inside the food, to 1, that means that there is a lot of free water inside the food. All the fresh foods have a high water activity, and with high water activity, bacteria can easily proliferate. So vegetables, meats, fish, everything. More processed food, on the other side, can have a very low water activity, and that this can help to control bacterial proliferation. Snacks or powdered milk, for example, they have a very low water activity, and that means that is almost impossible for bacteria to proliferate without free water. So that's why we created, for example, powdered milk and powdered food. But the most interesting for us growth influencing factor is for sure the temperature. The behavior of bacteria in response to temperature can be described by this curve. As you can see here, there are 3 characteristic temperatures that can be used to describe how microorganisms react to a thermal stimuli. That is the minimum temperature, the optimum temperature, and the maximum temperature. Below minimum temperature, bacteria cannot grow. They cannot proliferate if the temperature is lower than the minimum. They don't die, right? They stay alive, but they cannot proliferate. Basically, it's their cellular membrane jellifies, and they just keep a low level of metabolism without dying, but they cannot grow. Then there is this rise until this optimum temperature, that is basically the temperature at which the enzymatic reactions and all the reproductions of bacteria happen at an increasing rate. And so at this temperature, they can just replicate faster and faster and faster. After that, there is this drop. And for temperatures higher than the maximum temperature, basically bacteria start to die. Their proteins start to denaturate, and so they die. We can classify bacteria according to their behavior, to their thermal behavior. Pathogens usually are mesophiles. That means that they follow this green curve here. So basically, they have an optimal temperature around 40 Celsius. In nature exists many other bacteria that can have a higher resistance to the temperature, thermophile or hyperthermophile. Fortunately, they are not pathogens, or they are not very common. So basically, we should concentrate on these mesophiles, bacteria. And I also would like to introduce you a couple of metrics that can be used to evaluate and to describe thermal resistance. The first one is the parameter D. Dx is the time required for food maintained at a temperature X, in this case, to reduce the bacterial population by 90%. So, for example, D121 equal 0.2 minutes means that you need just 0.2 minutes if you keep the food at 121 to decrease the bacterial population by 90%. Please note that these temperatures are referred to the food. They are not the temperature of the environment. It is the actual temperature of the food. Another parameter can be used to describe and measure thermoresistance is this Z parameter. Here, the definition is that basically Z is the minimum temperature variation requested to obtain a change in the D value of 1 log. That, in other words, is the temperature variation requested to kill the bacteria 10 times faster. Here I report just some examples of the D value and the Z value for the most important pathogens that can contaminate food. For example, Escherichia coli is one of the most dangerous bacteria for food. They have a D value of 0.2 minutes at 60. That means that you just need 2.2 minutes to decrease by 90% their number at 60 Celsius. And the Z value of 5. That means that if you increase from, let's say, 60 to 65 the temperature, you need 10 times less time to decrease their number by 90%. So they are very thermosensible. Let's talk a little bit about this Bacillus cereus. They are more thermoresistant. You need 2 minutes, 10 times more at 60. Clostridium perfringens is one of the most dangerous. It can really almost proliferate at also at temperatures like 52, 53. You need at 65, for example, at 60, you need 2 minutes to decrease their number by 90%. And these are particularly tricky, Bacillus cereus and Clostridium perfringens, because they can create spores. A spore basically is a sort of status that a bacteria can activate when it finds itself in a environmentally dangerous situation. For example, a low amount of nutrients or an increasing temperature. They can evolve into this spore that basically it's a sort of shield that the bacteria can create to protect itself. And spores are very difficult to be killed. In the case of Clostridium perfringens, you need 20 minutes at 90 Celsius to kill the spores. Spores, they are not dangerous itself because they cannot proliferate when the bacteria evolve into a spore, cannot proliferate. And if you ingest spores, they are not dangerous by itself. The danger is because from the spores, they can evolve 1 time more into the vegetative form, that is the natural form of a bacteria that allow the bacteria to proliferate, and that in the case of a pathogen is dangerous for human health. So from what I have said, you can, I think, easily understand that since a vario works always in a temperature range higher than 62, 63, depends on the countries, it is intrinsically safe from a microbiological point of view, because it's always outside the danger zone. And as I showed you before, with respect to a fridge with respect to the cold chain, it guarantees that the bacteria are killed, because a Vario works at the temperature that is higher than the maximum temperature, as I showed you in the curve before. And for these temperatures, bacteria are killed. In the cold chain, you can just stop the bacterial growth. So basically, I can synthesize everything, just saying that if the food was safe after cooking, it will be just as safe or even safer after holding it in a Vario. To validate this statement, we performed a lot of tests. Actually, I just want to cite and to mention a couple of them with a third-party lab, Calab is the name. We prepared some food, a sort of pie soup, rice with tomato, lasagna, meatballs, and we measured after the product has been stored for 7 days in 3 different conditions: at -18 inside the freezer, at 4 Celsius inside the fridge, and inside the Vario. So 7 days. A Vario, these tests were performed at 62 Celsius. In the case of mesophilic microorganisms, Escherichia coli is one of them. As you can see here, while the food preserved into the fridge here and into the freezer, in the 25% of the cases, showed a number of bacterial colonies higher than what the guidelines asked and prescribed. In the case of a Vario, basically 75% of the time bacteria were not detectable. 25% of the time they were detectable, but their concentration was lower than what the guidance prescribed. In the case of enterobacteria, the situation is similar. In a Vario, you have 100% of undetectable. In the case of the freezer and of the fridge, you have, in the case of the freezer, for example, 13% higher than the guidelines. So this test just corroborated what we already knew from the science and from the microbiology, as I have tried to explain you before. Another interesting characteristic of a Vario is that it can also ensure safety by repasteurizing food when, for example, a thermal abuse, when, for example, the food go under a thermal abuse. So what we did in this test, we performed this test in the University of Parma, in the Department of Food Science. I'm sorry, this slide is in Italian, but I think that can be easily understood. We prepare, for example, this is a lentil soup. After storing for 5 days at 70 Celsius, you have less than 1 colony forming unit. That is the metric we use to say if we have bacteria or not. So less than 1 means no bacteria, basically. After that, we put the food for 36 hours at room temperature, just to trigger bacterial proliferation. As you can see in the lentil soup, after 36 hours at ambient temperature, we had actually 2.60 colony forming units. That means that bacteria, in this case, have actually proliferated. But after putting for 24 hours more inside the Vario at 70, we recovered a situation in which there are no colony forming units. So we have less than one colony forming units. So that means, and that this is a feature that we have implemented in the software, that if, for example, there is a electrical blackout and the Vario cannot guarantee a safe temperature, a Vario can anyway record the time of this blackout and can automatically calculate the repasteurization time once the electric current comes again. Okay, so there are many different regulations inside the world. For example, this is FDA in US that ask and that state that food can be safely preserved at temperature higher than 57 Celsius. This is another department in the US that asks for 130 Fahrenheit, that are 59 Celsius, I think. In Ireland, regulations are more ask for a higher temperature, 63. This is the World Health Organization that state that above 60, everything is safe. This is a European norm, 60. UK is like Ireland, is 63 Celsius. So basically, this is just to testify how also different regulations you can find in different countries in the world ask for what we have in our experiments demonstrate about the Vario safety. We also get a very important certification from HACCP International that certify that our equipment is safe and has been designed according all the guidelines that HACCP prescribe about food safety. This is a very important third-party recognition of our appliance. And that's it for the food safety part. I would like to conclude this presentation, just mention another important aspect, that is a question that many times our customer have asked us about the nutrients, how nutrients react to a Vario's, to holding inside the Vario. Nutrients basically are vitamins. The scientific fact is that the vitamins degrade during the cooking process. So the holding inside the Vario does not have any impact on the nutritional properties of food if the food has been cooked before to be held inside the Vario. To demonstrate this, we prepared some samples, was meatballs and chicken curry, something like that. These are the recipes. We prepared 2 batches for each food. One batch was preserved inside the Vario for, I think, 2 days at 65 Celsius. Second batch was preserved inside the fridge. What we found was quite surprisingly, because we found that in some type of vitamins, like vitamin A, for example, was less degraded inside the Vario than in the fridge. In other cases, like all the other vitamins, basically, there were no difference between the amount of vitamins in the food stored inside the Vario and the amount of vitamins in the food stored inside the fridge. So the conclusion of that is that holding inside the Vario does not affect the nutritional values of the food. Perfect. That's all from my side. If you have any question, there is some.
Thank you, Mario. That was really informative. Thank you. It's for me, it's a bit over my head because I'm not that into the technical, but hopefully those people that have been on the call have been able to understand that. So yeah, I'd like to thank you for that. We're going to go to the Q&A in a moment, but I just want to mention a couple of things before we get to that. So thank you both, Trevor and Mario, for the insight into the